Hello, I think I'm off. Are we off? Hello, everybody. Welcome to our web class. I'm just going to sort my screen out so that I can see what's happening with everybody. But hello, please feel free to say hi in the chat. Hopefully that is about to go full screen so we can see. There we go. That's what I wanted. Lovely. Hello. Welcome. This is one of our A-level web classes, A-level revision Sunday sessions. So this is chemistry, this is A-level chemistry, and today we're going to be looking at what is, I guess you would consider it to be primarily a year 12 topic because it's covered first in year 12, but obviously a very useful topic for both year 12s and year 13s because it is consistent pretty much across the whole of the A-level chemistry course. So this is calculating reacting masses. So hello, welcome. If you are new to our Sunday sessions, then lovely to have you here. If you are a regular, then lovely to have you back. Welcome back. Please feel free to say hi in the chat. We'll use the chat as we go through the session for me to kind of get answers from you guys, but also for you guys to give each other answers to one another. So hello, Annabella, lovely to have you here. Feel free also to tell me what year you're in as well, because that gives me a good idea of what, where we're basing our sessions, whether we should be, how mean I can be basically with getting answers from you. Hi, Sophie, lovely to have you here as well. And hi, Mia, you're a year 12, awesome. Very good. It's really good if you're a year 12 to be already thinking about doing a bit of revision, because if you haven't already been revising, now is a good time to kind of start revision of your year 12 content so that when you start the second topics in A2 and you build on your year 12 knowledge, you know where your weaknesses are, you know the bits you need to concentrate on and the questions that you need to ask. So really good. So well done. Okay, Annabella, you're year 12 as well. Lovely. Z, you're year 13. Well done. Good. And apologies if I get my name, if I pronounce names wrong, it's entirely my fault. But is it Suhaila? That's lovely. Oh, Annabella, you're year 13. Oh, fair. Great. So this is quantitative. It is definitely quantitative. So what we're going to look at actually are we're going to look at the basis of content from calculating reacting masses, and then we're going to spend probably a decent chunk of our session going through 2 exam questions, which are typical exam questions, but also can be a little bit tricky for some people. So that's what we're going to be spending our session doing today. I think we'll get started just because if anybody else arrives, please feel free to say hi in the chat. Lovely to have you here, but we'll get started. And in order to do that, I'm just going to need to flip my laptop around so I can write on it. When it does that, sometimes my video cuts out. So I'm just hoping that it's going to play ball today. And it seems to be liking me today, so that's good. Okay, awesome. So A-level chemistry web class, this is calculating reacting masses. If you haven't already, please feel free to download the slides which are in the description below, because you can write on them, you can save them for revision, you can do whatever you want with them. So please feel free to do that. You can save it, you can scribble on them now and then save a separate copy to revise from later. They're super useful. So please do that. The link should be in the description for you. And yeah, let's get started. Okay, so this is a little bit about me. I have been teaching chemistry for over 7 years now, or teaching science, but chemistry is my specialism because chemistry is good. It's my favourite. Oh, hi, Abby as well. Welcome, Abby, and Muna. Lovely to have you here. And Sham, brilliant. Welcome too. And Zika, lovely to have you here as well. Fabulous. So I have a PhD in chemistry from Oxford, or science, but specialising in chemistry again. And I'm the lead chemistry teacher here at SnapRevise. One of the exciting opportunities that we've got coming up actually at SnapRevise, if you're interested in doing a bit of revision, especially with SnapRevise, then we have these crash courses. So they are 1-day seminars, 1 day for year 12, 1 day for year 13. So if you're a year 12, you can still come along to the year 12 one. And they are to try and help you get 100% exam ready. We look at exam technique, we look at trickier topics, we print out an amazing seminar booklet which has loads of information, loads of stuff to revise from, and loads of exam questions to have a go at. And then we also, if you come along to one of our sessions, you have access to what's called a tutor messenger. So, and I'll explain a little bit about what these are, a little bit more about what these are at the end of the session. So if you're interested, then hang around and we'll cover a little bit more about this in the end of the session. But just so that you know that we are doing seminars in 4 topics, four subjects: biology, chemistry, physics, and maths. And they take place either in person. So if you're a London-based person or you want to travel into London for an exciting day or two, then they are happening in person at Regent's University in London. Or if you can't travel into London, so you're based elsewhere, or you just don't fancy leaving your bedroom, fair, then you can also live stream these events. So this is, we're literally going to be filming the event in Regent's University London, so you can live stream onto it. Good questions, guys. I'll come to those in a second. They're happening in the Easter holidays. At the end of the session, we've got some information about it. I wish it was free. If we could offer it for free, we would, but we can't, unfortunately. We do these Sunday sessions for free, but the seminars you do need to pay for. They're slightly different prices for online versus in person, so feel free to have a look at that. And if you're interested, please head over onto the SnapRevise website, where there'll be loads of information about the seminars that you can have a look at. But it's really, really worth investigating if you're the kind of person who works well with crash courses, because we will be covering as much as we can of the AS and A2 syllabuses in one whole day. So one day on year 12 and then one whole day on year 13. So feel free to have a look at that. Like I say, I'll put some more information about this up at the end of our session today. So to come back to what we're doing now, what exam board we're covering. So actually in our A-level crash courses and today in our web class, we cover all 3 of the main exam boards: OCR, Edexcel, and AQA. So if you are one of those 3 main exam boards, then we cover all of those topics. The overlap between the exam boards is pretty huge, but if there are any major differences, which there are some things that are included in some, not in others. There's some phrases that you use specifically for one exam board but don't use in the others, etc. Then we will point them out to you. So we do try and highlight as much as we can of what's different between the exam boards when there are differences. But most of the time, the content is pretty similar between the 3 exam boards. So in this session, we will be covering all 3 exam boards. And in the A-level crash course, we cover all 3 exam boards. So it's for everybody. As much as we can, it's for everybody. Okay. Just a brief note about online safety. Just make sure that you are being safe online. If you choose to link up with people, we don't endorse that at SnapRevise. Okay, so today then, let's do this session. Today we're looking at recalling the formula, linking moles, concentration and volume. That's something that hopefully you did at GCSE, but we also do again at A-level. We look a little bit more detail, we apply it to more situations. We're going to look at performing some calculations using moles, concentration and volume. And we're going to look at calculations using both mass formulae and the concentration formulae as well. We're not, however, going to look at ideal gas today, which is something that's linked quite closely in this topic. That's covered in a separate web class. So we don't cover that. We're not going to cover that today. So just to reassure those of you on the different exam boards, if you're an AQA specification follower, then these are the spec points specifically from your spec that we are going to be covering, so you can match it up with your spec. If you are OCR, these are the spec points that we're going to be covering from yours, but bear in mind, we're just not going to be doing ideal gas. I'm sorry, I should have pointed that out on that little one there, not volumes of gases, because we're not doing the ideal gas law. Apologies for AQA. So OCR, we're going to be doing this, but not the gas volume bit. Obviously, you do need to do it, but it's not covered in this web class today. And then Edexcel, again, these are the spec points we're going to be covering, but not the volumes of gases, which is that one there. Or those 2 there. Unfortunately, we don't do WGEC, although again, there is a huge amount of overlap. So if you're somebody who's confident with your spec, if you print out your specification and have it in front of you or nearby, you're welcome to join these classes because the content is hugely overlapping. And then you can just double check if it's on your spec and the wording that's written on your spec, for example. So it's still going to be useful for everybody, but we just don't kind of specifically check the WJEC or the A levels either. Okay, so let's get started. So one of the main points, one of the particularly useful bits about doing a class live is that you can engage your thoughts and try and get yourself remembering things as if, not as if we're in an exam, but, you know, engaging those memory recall pathways. So let's have a think about what we already know and how we can work it out if we don't. What's the definition of a mole? Can you have a go at typing the definition of a mole in the chat? And if somebody gives one that you agree with, feel free to just agree with them. If somebody gives something and you want to slightly change the wording, you can just add some extra wording. But what are we thinking? And if you don't know a definition, are there any keywords, phrases, numbers, equations that you could suggest that will help us to remember what a mole is? What is a mole? What is this weird concept that we're introduced to technically at GCSE, but we look at in more detail in A level? Does anyone know? Oh, Catherine, great. Yep. Good, CL, lovely. That's a very useful. And root, that's really good as well. Good. So it's a standard unit of an amount of substance that contains Avogadro's constant number of particles. Really, really good, guys. That's awesome. So a mole is the amount of substance that contains Avogadro's constant number of particles. Number of particles. If at any point you can't read my handwriting, please feel free to let me know and I can write something again. I am quite good at noticing when something is illegible, but feel free to tell me if you can't read anything. And of course, if anybody at any point has any questions, just pop them in the chat and I will try to come to them. If I miss them, it's probably because it's disappeared off my screen, so feel free to send it again. So that number, as is written in our chat, brilliant, is 6.023 or 22, depending on how you want to round it, times 10 to the 23. I am actually going to give it as 022 because I think that's what OCR have to give it as. So I'm going to give it as 022. 6.022 times 10 to the 23 particles of a substance. Brilliant. So, your link to carbon 12, you're thinking, is it a good thing to link it to? But it's only linked to carbon 12 when we talk about relative atomic masses. So here we're just talking about a mole. Now, there is a lovely, it does link, I want to say serendipitously, it does link to relative atomic masses, but that is almost a happy coincidence or a very well thought out mathematical coincidence, unfortunately. Yeah, exactly, that's for relative atomic mass. Okay, what about conversions? We need to be really good at converting from decimeters cubed to centimeters cubed and back again. So how many centimeters cubed are there in a decimeter cubed? Does anybody know? Well done, guys, you are on it. Fantastic, it is 1,000. Really good. If you're ever not sure, I always break it down because the cubed bit is just 1,000. The cubed bit sometimes confuses people. So go to 1 decimeter in centimeters. So 1 decimeter is 1/10 of a meter. So a decimeter is 10 centimeters, because a decimeter is 1/10 of a meter. So to go from just decimeters to centimeters, we've had to times by 10. So to go from decimeters squared to centimeters squared, we have to times by 10 squared, which is our 1,000. So just in case you're not sure. And okay, brilliant. So what is 1 decimeter equal to in terms of liters? Does anybody know? What is 1 decimeter equal to in terms of 1 liter? It is just 1. Good, well done. It is just 1. So 1 decimeter is 1 liter. A nice easy link there. And this is why we like to use decimeters, because it has an easy link to liters, which is kind of a more common casual volume unit. So we like to use decimeters when we're measuring things, because it has this link to litres, which is going to be very useful. Brill, really, really good. Well done. That's a 1-to-1. What about molar mass? So common misconceptions come up when we talk about molar mass, molecular mass, atomic mass, formula mass, all of these masses, which sound very similar, but do have very specifically different definitions. What's the definition of a molar mass? Because this is the definition that we should probably get most used to using, because it's a bit more of an umbrella term, and it means we shouldn't end up being scientifically incorrect. So what is molar mass? Break down the phrase. It's molar mass, so it would be mass of 1 mole. So the molar mass is the mass of 1 mole of a substance. Now that substance could be an element, that substance could be a compound, that substance could be a molecule, that substance could be an ionic compound. If we use the term molar mass, it's an umbrella term, it means it's a cover-all. So this is a great question. Is it the same as relative atomic mass? You can be talking about the molar mass of an element, which colloquially, casually, we might say is the same as relative atomic mass, but the relative atomic mass is actually a very specific number. So they're not technically, it's not the same, but you can use molar mass in the same situation that you might be using the term relative atomic mass. Hopefully that makes sense. So molar mass is the mass of 1 mole of a substance. So yeah, you could do the mass of a substance, of an amount of substance divided by the number of moles in that substance, and that would give you the molar mass. Very good. And relative, yeah, again, so Annabella, relative molecular mass, you need to be careful with as well, because it's technically not the same, because relative molecular mass is the mass of 1 mole of a molecule, of a molecule, a molecular substance, relative to 1/12 the mass of a carbon-12 atom. So again, much more of a specific definition, whereas molar mass is much more of an umbrella term, and we can use it much more loosely, and it is much easier to use and not be incorrect, basically. So it's what I will try to use most of the time anyway. Okay, so let's have a look at moles, concentration, and volume. Oh, this is a nice little practice for you then, pre your chem mock. That's good. Well done, you. So if you're an equation triangle person, great. Not everybody is, but then this is our equation triangle. Moles can be calculated from concentration and volume. If moles, the unit is mole, concentration, our unit is mole per decimeter cubed, and therefore our volume needs to be in decimeter cubed. This has probably been drilled into you that we need to make sure we have volume in decimeters cubed, not per decimeter cubed, decimeters cubed. If ever you're not sure though, I think it's really useful to use concentration to work out what your equation is, because concentration is moles per decimeter cubed. So concentration is moles per decimeter cubed. So if we think about what that means the number of moles over the volume. So we've got our equation there, concentration is equal to moles over volume, which is correct. So you can use that to put it into your formula triangle, or you can just rearrange that as an equation. Looks like some of you have done brilliantly in having a go at calculating the number of moles of HCl in 50 centimeters cubed of a 5 mole per decimeter cubed solution. So first step is usually to convert. So really well done, Hamza. I think you noticed it, and lots of other people seem to have done it already brilliantly. So we have to convert to decimeters cubed. Whoops, convert, not convert. Convert 50 centimeters cubed to decimeters cubed. And so to go that way, centimeters cubed to decimeters cubed, we divide by 1,000. So well done those of you that did that. I think It looks like lots of you already have because you've all got correct answers, which is great. So 0.05 decimeters cubed. And then we're trying to work out number of moles. Moles is equal to concentration times volume, as long as volume is in decimeters cubed. So our concentration is 5 moles per decimeter cubed. Our volume we've just worked out is 0.5 decimeters cubed, which means we end up with 0.25 mole of HCl as our final answer. Can you just multiply the two numbers and divide by 1,000 instead? If you multiply 50 and 5, you then have to times by 1,000. Let me just, no, you don't. No, yes, you're right, you can. Yeah. Sorry, I'm getting myself confused. Yes, absolutely right. Merit, well done, yeah. Sorry, I've just seen we've got lots of things going on in the chat, just checking I haven't missed anything. So just as this is a slightly an aside tip, but with titrations, if you are someone that struggles with titrations or the big moles questions, one of the tips that I'm going to give you or that we're going to do together in a minute is to draw them out, make it pictorial, because I think it's much easier to then work out what information you've got and all that sort of thing. So if you are somebody that struggles with titration questions, I will always draw them out and try and work out the process, what's happened, how you've got from A to B, what numbers you've got, what numbers are missing, and then work backwards through it. So yes. And yeah, and Dema, that's a really nice tip as well. There's often a formula to work out something, and then you've got to think about ratios to work out something else, and then you've got a formula to work out something else, or maybe another ratio perhaps. And yeah, nice way to think about it. Cool. Okie dokie, well done guys. So 0.25 mole HCl there, bro. That's just like a typical easy. I know none of chemistry is easy, is it? None of A-level chemistry is easy, but this is a simpler exam question. They're more likely to appear like this, which are more of our reacting masses. So please feel free to have a go and come up with answers for those two. So this is my question A, this is question B. So if you wanted to have a go and just power ahead, see if you can come to an answer. We'll see if we agree. I'm going to work through it semi-slowly. So A says, KCl reacts with a 3 mole per centimeter cubed solution of AgNO3. Just as a tip, if you don't already, I like to highlight any numbers, concentrations, volumes, masses, moles, anything like that, because the likelihood is you're going to come back to them later, and it makes it really easy for you to find them in the text if you underline them. So then they've asked us to calculate the volume in decimeters cubed of silver nitrate solution needed to react with 10 moles of KCl. So what volume in decimeters cubed of silver nitrate solution is needed to react with 10 moles of KCl? So again, feel free to jump ahead, have a go, plug some numbers into your calculators and see if you can come up with an answer. To begin with though, I think it's useful to work out what information we've got. So we've got 10 moles of KCl. We're looking to work out how much silver nitrate we need. Well, we've been given in our equation a ratio of 1 to 1, 1 lot of KCl to 1 lot of AgNO3. So if we've got 10 moles of KCl, then because it's a 1 to 1 ratio, we're going to need 10 moles of AgNO3 because they're a 1 to 1. Which means we know our amount of silver nitrate. So if we know our amount of silver nitrate, and we've got a concentration as well of silver nitrate, so we can work out a volume. Volume we know is equal to moles divided by concentration. So moles we worked out are 10 moles. Divided by our concentration, which is 3 mole per centimeter cubed. Now, I am a big advocate. I know that it takes time and I know that it's annoying, but I really do recommend using your units and writing units in, because A, you can work out if you've made a mistake a little bit easier, because here I can tell that when I divide my moles by my moles per centimetre cubed, I'm going to end up with centimetres cubed, which is a volume, which is what I want. If I've done it the wrong way around, or I've times it, you can see a bit easier whether or not you're going to make a mistake. So it's worth, I think, using your units. It also reminds you, for example, here, because I wrote my unit in, I've got it in centimetres cubed. Just because, so that's a good question. Why is it mole per centimetre cubed? Because this is what the question's chosen to give it in. They want us to do some converting. So they've given it to us in an awkward unit. So we have to do some converting ourselves. That's all. So, but good question, good notice. So yes, it is in centimetres cubed. So that means the volume I get out is going to be in centimetres cubed. And they've asked for it in decimeters cubed. Amara, that's a very good question. The unit here is mole per centimetre cubed. So mole divided by centimetres cubed, which is equal to mole centimetres to the -3 per centimetre cubed. So because I'm writing it, I've already got it in a fraction over there on the right. I'm going to write it as the -3 because to my brain, that makes more sense than writing it as another fraction in a fraction, because fractions in fractions are awkward and can be slightly confusing. So personally, I would always write it as to the minus, just to help visually, to help see what it looks like, and that hopefully that makes sense. Lovely. Okay, so I'm just going to rub out that at the bottom because I need the space. So then we've got, well done those of you that have had a go already. That's brilliant. So we've got 10 moles divided by 10 moles per centimetre cubed gives us 3.3 recurring. That's not a very nice number, is it? Centimetres cubed for volume. But the volume is in decimeters cubed. So how do we go the other way? How do we get our volume of silver nitrate in decimeters cubed? To go from centimeters cubed to decimeters cubed, we need to divide by 1,000. So it ends up being 3.3, well done, well done. 3.3 times 10 to the -3, or 0.00, yeah, 0.003, 3333 times 10 to the -3, that's supposed to be decimeters cubed. Oh, Amara, that's a good question. Give me a second. Is centimeters cubed the same as 1 over centimeters to the -3? I want to say yes. Yes, it is. Yes. Because it's 1 over centimeters to the -3. Because centimeters to the -3 is 1 over centimeters. So it's 1 divided by 1 over. So 1 divided by 1 over 1 times by, yes. Yeah, it is. Yeah. My brain is not a mathematical brain. So that took me a second, but yes, I think you're right. Okay, part B then. We've also got someone who's given us an answer already, which is fabulous. Let's just whiz through it because I'm already a couple of minutes late. Never mind. 0.35 moles of lead nitrate reacts with 100 centimeters cubed of HCl. Again, I'm underlining my key bits. You're right, Hamza, we could convert moles per centimeter cubed, but the confusion comes when it's moles per centimeter cubed. You have to make sure that you're doing the right conversion from centimeters cubed to decimeters cubed, whereas converting from centimeters cubed on its own, not per centimeters cubed, just centimeters cubed to decimeters cubed, is easier for a lot of students. So personally, I would always convert the straight units rather than a per unit, because then you're dividing by centimeters cubed. So in order to get to decimeters cubed, you would have to times by 1,000. So your 3 mole per centimeters cubed would become 0.003 moles per decimeter cubed. And are these live saved on the YouTube? Yes, they are. So please feel free to go back and have a look at them. And you can download the slides, hopefully, from those as well. And if you can't, just drop us a message and we'll hopefully try and get the slides back up for you. but you should be able to absolutely go through all of these lives from the last couple of years, even, I think, unless they've been taken down recently. They should all be up there. Okay, so calculate the concentration of HCl in moles per decimeter cubed. So what information have we got? We've got moles of lead nitrate, and we're reacting with an amount of HCl, so we need to know the concentration of HCl. So always thinking amounts is useful. If I've got 0.35 moles of lead nitrate, my ratio is 1:2 lead nitrate to HCl. So that's 0.35. No, let me do that better. So if it's a ratio of 1:2, and we've got 0.35 moles of lead nitrate, then we're going to need 0.7 moles of HCl. I'll come to your question in a second, Amara. I'm just going to finish this one. So our moles of HCl is 0.7, 2 times 0.35. So that's how many moles we need to react with our lead nitrate. We need that many moles in 100 centimeters cubed, but they want the concentration in decimeters cubed. So I can convert my volume to decimeters cubed. So I've got it in decimeters cubed. Again, I personally would prefer to do it while it's just a straight volume, not a concentration, because it's harder to make a mistake. So 100 centimeters cubed is 0.1 decimeter cubed. So the concentration of HCl is moles divided by volume. Oops, come on, pen. Moles divided by volume, which is 0.7 divided by 0.1, which means our concentration is 7 mole per decimeter cubed. Very good. Well done, those of you that got that. That's awesome. 7 mole per decimeter cubed. Okay, I'm not sure if this question makes sense, but why in some questions are you meant to ignore the big numbers next to reactants and products? It depends. It's a good question, Amara. It does take a little bit of getting your head around it, because you really have to understand, I think in order to fully understand these questions and be able to tackle pretty much anything, you really need to understand what the numbers are that you're calculating. So in my head, I have it very separate. I have, these are the ratios of reacting amounts. So if I wanted to react exact amounts, this is how I would do it. And this is using the balanced equation. And then I also have in my head, right, this is what I've got at the moment. In this experiment that I'm doing, these are my amounts. So the reacting ratios are really useful for working out what would react with what and what can react with what. You also then need to be aware of what do I actually have, and then I can use my reacting ratios to work out how they would react. But in my head, it's a very different thing. They're separated in my head from a practical experiment. This is what I'm doing now, and these are the perfect ratios of reacting amounts. So that when you're trying to use your ratios or not, in my head, I'm thinking, right, am I using my perfect amounts? Or am I looking at what actually I've got in front of me now and how they relate to one another? And that can hopefully help you maybe to work out when you ignore those numbers and when you don't, or maybe not ignore, when you use those numbers and when you don't need to use those numbers because it's not relevant or appropriate. It's not an easy thing though. And I'm just, for everybody, I would say practice, practice, practice. Practice makes perfect. So like I said, we are a couple of minutes behind schedule with this, so apologies for that. It's just because I like talking. So just give me a quick number or a smiley face to let me know how confident you're feeling about that topic. It's good for you guys to register and kind of learn how confident you're feeling and kind of just take a second to think about it. Yeah, I'm feeling confident about this, or no, definitely need to revise this. This is horrible. But also it's good for me to know how we're doing. So give me a 1 or a smiley face if you're feeling, yeah, that's quite straightforward. You can give me a 2 or a middly face if, yeah, well, it'll be all right, maybe. I think I need to do a bit more work on it. Or you can give me a 3 and a if this is horrible and I hate it and I never want to see it again. But unfortunately, you have to because you're doing an A-level in chemistry. Awesome, lovely, that looks good. Okay, so we will have a whiz through this question. again, feel free to zip on ahead because this is a long question. So we're going to try and get it done ASAP. Amara, if we've got time, I'd absolutely love to. We are going to be a little bit short for time on this session because I already have a load of stuff I'm supposed to cover at the end already anyway. But if we have time, I will happily stay for a couple of minutes and just go through it with you. Okay, so here we go. This is talking about horrible titration questions. This is a nice horrible titration question. Have a quick read through. I'll read it to you now as well. And I'm going to, using my pen, highlight bits of information that I see as I come across them, because it's really useful, especially when you've got a question like this, where there's a lot of information thrown at you at once. Really useful, I think, just to make sure that you separate out those key numbers, which you're likely to want to refer back to. So a student was given 200 centimeters cubed of solution X, in which sodium hydroxide, NaOH, and sodium hydrogen carbonate, NaHCO3, had both been dissolved. Yes, titration, exactly. The student carried out 2 different titrations on samples of solution X, 2 different titrations on samples of solution X, using 1 mole per decimeter cubed sulfuric acid. In the first titration, both sodium hydroxide and the sodium hydrogen carbonate were neutralized. In the second titration, only sodium hydroxide was neutralized. The student's results for the titrations of 25 centimeter cubed samples of solution X are shown in the table. The volume of sulfuric acid needed to neutralize both was 29.5 centimeters cubed. The volume of sulfuric acid needed to neutralize only sodium hydroxide was 18 centimeters cubed. Then we have 2 reacting ratios, 2 balanced equations. And question AI says, calculate the amount in moles of sulfuric acid used to neutralize only the sodium hydroxide in 25 centimeters cubed of solution X. Feel free again to jump ahead and come up with an answer, but what are we thinking? What are we thinking? Anybody got any ideas? I want to know the moles, the amount in moles of sulfuric acid that was used to neutralize only sodium hydroxide in 25 centimeters cubed of solution X. If I'm looking at only sodium hydroxide, if I look back at the bits of information I've got a volume of H2SO4 needed to neutralize only sodium hydroxide. So I've got, oh, that looks promising. I've got a volume of sulfuric acid of 18 centimeters cubed. They want an amount in moles. So I've got a volume and I'm trying to work out moles. The thing that links them, or that would be useful to have, is a concentration. Do I have a concentration? Yes, I do. That was earlier in the question. Very good. So moles is equal to concentration times volume, or volume times concentration, however you'd like to put it. And making sure that the volume is in decimeters cubed, not centimeters cubed. It looks like you've already done that, Hamza, which is great. So my 18 centimeters cubed is going to be 0.018 decimeters cubed. Very good. I'm going to write that in up here at the top. So moles equals conc times volume. My concentration, we've said, is 0.1 moles per decimeter cubed, times by, that doesn't look like per, let's try that again, times by the volume, which is 0.018 decimeters cubed, means our answer is 1.8 times 10 to the minus 3 moles. Okay, Hamza, very good question. What about the 25 centimeters cubed? This 25 centimeters cubed is of solution X. So I have my solution. This is where I was talking about drawing a picture, if you're unsure. I have my solution X. I had 200 centimeters cubed of solution X. I carried out 2 different titrations on 25 centimeter cube samples of solution X. So I've got one 25 centimeter cube sample of solution X, and that's my titration, H2SO4, and that needs to go out the way. I had another one. Oh, my pen's being silly. There we go. Another 25 centimeter cube sample of solution X. And it's been titrated again with H2SO4. And my amounts are given below. The 0.1 came from up here. In the information of the question, it told us that it was 0.0100 mole per decimeter cubed solution of sulfuric acid. So they gave us a concentration already of sulfuric acid. Good question though. It's useful. These are the kind of questions which help you to piece together our exam questions. So I don't need to use 25 centimeters cubed of solution X because at the moment, this is just to go back to Hamza's question, I'm only interested in the moles of H2SO4. So all I need is a volume and a concentration of H2SO4. That's all they've asked me about. In part 2, if we have a look at part 2 now, it says, oh, so I've got bits all over my screen that need to move out of the way. It says, calculate the concentration in moles per decimeter cubed of sodium hydroxide. Oh, no, that's not supposed to happen. Try again. Okay, of sodium hydroxide in solution X. So now I'm thinking about sodium hydroxide in solution X. So this, going back to your words, Amara, to your question even earlier, in my actual solution, I'm trying to work out the concentration of it. Practically, that's what I'm trying to find. So what have I actually got? Well, I don't have any information about sodium hydroxide yet. I only have the 25 centimeters cubed because that's my volume of solution X. So I need to find out a concentration or, no, sorry, I'm calculating concentration. I have a volume, I need to find out moles. So concentration is equal to moles over volume. I've got the volume because I know my volume of solution X is 25 centimeters cubed because I was told that in the question. So I need to find the moles. So how do I find the moles? Well, I know I had 1.8 times 10 to the minus 3 moles of sodium hydroxide, sulfuric acid, sorry. 1.8 times 10 to the minus 3 moles of sulfuric acid. So how much sodium hydroxide must have reacted with it? And how do I know? I've got sulfuric acid amounts. I want sodium hydroxide amounts. How do I link the two? This is where I can use my reacting ratio. So again, thinking about slightly separating it in your brain. Now I can think about that. You can't see the working in, can you not? Sorry, is my picture in the way? All I wrote was 25 centimeters cubed. Let me just move that. Thank you for pointing that out though. 25 centimeters cubed. Thank you for pointing that out. So I need to use my reacting ratios. So if I have one lot of sulfuric acid, I will use up 2 lots of sodium hydroxide. So they are in a 2-to-1 ratio. A 2-to-1 ratio, which means I always have, it doesn't matter which way around you think of it, but I'm going to think about it in terms of I will always have twice as much sodium hydroxide as I have sulfuric acid. So if I have 0.18 times 10 to the minus 3 moles of sulfuric acid, I must have twice as much sodium hydroxide. So my moles of sodium hydroxide must be twice that of my sulfuric acid. Oops, let's move that out of the way now. Moles of sodium hydroxide are twice the moles of sulfuric acid. So I'm going to need to double, not divide by 2, double my moles of sulfuric acid. So 2 times 1.8 times 10 to the minus 3 gives me 3.6 times 10 to the minus 3 moles of sodium hydroxide. Got to be so careful with the words, haven't you? So that now I've got a moles of sodium hydroxide and I've got a volume because it's my amount of sodium hydroxide in solution X and the amount of solution X that I'm using at the moment is 25 centimeters cubed. So I get 0.144. Well done, those of you that got that. That's brilliant. 3.6 times 10 to the minus 3. Again, I'm just going to write out all of my units. So it's going to make it a bit squished, but never mind. I'm converting to decimeters cubed. Well done, those of you that already did that. We must make sure we do that. And therefore, we get 1.44 moles per decimeter cubed. Sorry, I said 1.44, 0.144 moles per decimeter cubed. And then part BI then says to calculate the amount in moles of sodium hydrogen carbonate. So how am I using that? How do I do that? This is where there's a little bit, this is where the deeper understanding comes in. This is where those of you who are working at kind of an AA star level will probably find it easier to notice this or to work this out. Most of us will need to just take a second to puzzle it through. We use the second titration to work out all of those previous informations. I know, Amara, it does. I will just reassure you that one of the reasons why this will only be worth 1 mark each, even though there's a fair bit of calculating to do, is because earlier in the exam paper, they would have given you more marks for doing the same sort of process. So when they come to ask it of you again, it'll only be worth 1 mark because they've already given you marks for the process. So it's slightly unfair us doing these questions in isolation because you don't always get given the same amount of marks as you would otherwise. But you know, in an exam, these questions would only be worth 1 mark because earlier in the paper or later in the paper, you will be given, 1 mark for using your reacting ratios, for example. Similarly, this next bit is only worth 2 marks, and there's actually quite a lot of working that we're about to do. So again, later or earlier in the paper, you would be given more marks. So, good thought, Hamza. There's definitely a little bit of juggling we need to do, but you're not quite using the right numbers, but you've got the right idea. I think you're on the right lines. We've got 2 titrations. One where it neutralized both sodium hydroxide and then also was able to neutralize sodium hydrogen carbonate. And then our second titration where we only neutralized sodium hydroxide. So we only put enough sulfuric acid in to neutralize the sodium hydroxide. So how much sulfuric acid is needed to neutralize just the sodium hydrogen carbonate? Yes, Amara, absolutely right. The volume of sodium hydroxide, get my words right, the volume of sulfuric acid that was needed to neutralize just the sodium hydrogen carbonate must be the difference between the two. You won't be the only one, Hamza. If it takes 18 centimeters cubed to neutralize the sodium hydroxide in our solution, then the rest of that, up to 29.5 centimeters cubed, must be to neutralize the sodium hydrogen carbonate. So although we've done it as 2 titrations, it's the same solution X that we're neutralizing in both cases. So the concentration of both will be the same. So the first 18 centimeters cubed of our 29.5 centimeters cubed will be just neutralizing the sodium hydroxide. And then the rest of it will be what neutralizes the sodium hydrogen carbonate. So what is that? 29.5 minus 18 is 11.5. My pen's being slow. So 11.5 centimeters cubed of H2SO4 is what neutralizes the sodium hydrogen carbonate. We're following a similar process to the one we did in part A. It's just we're now doing it for sodium hydrogen carbonate. So to start off with, we need the amount of H2SO4 that neutralizes only the sodium hydrogen carbonate. Then it becomes a simple, again, nothing in chemistry is simple, but a simpler process of concentration, volume, moles. Let's have a look. If we've got that volume of H2SO4, then we can work out the moles, because moles equals conc times volume. So our moles of H2SO4 needed to neutralize the sodium hydrogen carbonate is conc times volume. We know our concentration is 0.1 mole per decimeter cubed because that's given to us in the question. Times by our volume needs to be in decimeters cubed. So don't forget to convert to decimeters cubed. Oops, I missed a 0, sorry. Decimeters cubed. So our moles of H2SO4 used to neutralize the sodium hydrogen carbonate is, where's my numbers? 1.15 times 10 to the minus 3 mole. If anyone disagrees with me at any point, please let me know. Well done, Hamza, absolutely. That's our moles of H2SO4. How many moles does that mean we had, again, thinking back to our ratios then, how many moles would that mean have reacted with our sodium hydrogen carbonate? Well, again, it's a 2-to-1 ratio. We use our equation over on the left here. So it's a 2-to-1 ratio. So we must have twice as many moles of sodium hydrogen carbonate as we do of H2SO4. So we've got, you're so close, both of you. Just double check what's being asked in the question while you have a look at that answer. So we've got 2 lots of 1.15 times 10 to the minus 3 moles gives us the moles of sodium hydrogen carbonate, which is 2.3 times 10 to the minus 3. Running out of space. That is how much is in our titration. Yes, Amara, well done. That's in 25 centimeters cubed. They want the moles in 200 centimeters cubed. So how do we do that? How do we scale up to 200? You can do it via concentration if you want to do it via concentration, or, well done, Anna Ritchie, times by 8, exactly. So just to confirm it, we can work out how many times 25 goes into 200. That is 8 times, so we know that we've got to be 8 times bigger. So 2.3 times 10 to the minus 3. Oh dear, my pen's going funny. Mole times by 8 gives us our final answer of 0.0184 mole. And I'm just going to highlight that. As well, if it'll work. So that's my answer there, 0.0184 mole. So Gabriella, they asked us for the amount in moles in 200 centimeters cubed of solution X, but these numbers we were using up to that point were for a titration which only used 25 centimeters cubed. So we found out the amount in moles in 25 centimeters cubed. So we then need to scale it up to 200 because that's what they've asked us for in the question. Let me know if you're not happy with that. So that's the moles in 25 centimeters cubed of sodium hydroxide. So then we need to scale it up to 200. A common mistake, a common error, lots of students would have not scaled it up, and so will only probably have gotten 1 mark from that calculation, even though, as we said before, loads of stuff going on there. Right, I'm going to have to stop it there because we're running close to the end of time. So what I'm going to do is I'm going to give you the amounts, or the answers, sorry, for these 2 bits of the next part, and then the exam question on the end, so you guys can have a go at it yourself. Take your time to work through them, but you should hopefully get 28 moles per decimeter cubed to 3 sig figs for the first one, and then 0.129 decimeters cubed to 3 sig figs for the second one. So please feel free to have a go at those 2 yourselves, and make sure that you're happy with those. apologies, we haven't had time to go through them, but we, as often happens with that exam question, because it's quite a hard one, it does take a while to go through. So we haven't had time to go through it. There's another one which you may find easier, especially those of you that find titrations harder. This question you may find a bit easier. So again, please feel free to have a go through it. And the answer you should get to is 123 moles per decimeter cubed. So again, please feel free to have a go at those yourself. As you'll notice, just going back to our conversation, this whole thing is worth 5 marks, even though it's probably less working than the previous exam question. I know, Hamza, I'd love to be able to do more, spend longer on these, but this is why, if you're interested in these sessions, have a look at Snap Revise, come over and join us in some of our web classes. That would be lovely. So we've looked at the formula linking moles, concentration and volume. We've performed some tricky calculations using moles, concentration and volume. We didn't get to spend any time doing some calculations using just masses, but that's why we do volume first, because it's always, well, not always, it's often harder, especially the questions that you can go through are harder. So please feel free to have a go at those together. Before we do questions, I'm just going to go through our seminars, which we've got coming up in the Easter holidays, which I mentioned at the beginning of the session. So if you're interested in our A-level exam crash courses, we go through exam technique, we go through some of the trickier topics, we provide a seminar booklet, and we also have tutor messengers. So these are the things which are particularly good about our crash courses. So the exam technique, we spend a good hour every day, so in the year 12 day and the year 13 day, looking at exam technique skills, how to break down questions, how to interpret questions, how to interpret command words, what's important when you're thinking about answering questions. We look at the variety of different question types that come up in your exam, and we look at common errors from that students often do and how to tackle those. And we look at a step-by-step approach to writing full mark answers. So really useful start of the day is looking at exam technique. Then in our crash courses, we then look at some of the trickier topics. It's not possible, as much as we would love it, it's not possible to cover every inch of a full year-long course in one day. It's just not possible. We'd love to be able to do it if it were possible, but it's not. So what we do is we look at the trickier topics, the ones that students hate, the ones that students find particularly difficult, and we look at breaking them down and revising them, and using the exam technique skills that we did earlier in the day to tackle some questions on them. So we break it down, we put them in bite-sized chunk so that you can have a look at them. We provide these amazing booklets. They really are amazing. They're full of notes. They are full of questions and answers and bits for you to go through. So if you sign up to our crash course, you will be, if you're doing it from live streamed, so not in person, if you're doing it from live stream, then you will be posted the booklet to you. But if you're doing it in person, you'll be given your booklet on the day, so you can scribble all over it or keep it pristine, whichever you prefer. But you can complete it throughout the day, you can annotate it, you can do the questions. It's an incredible take-home resource, and it's got lots of extra stuff in there as well that we don't go through on the day that you can just take away with you. And finally, one of the things that we provide on these crash courses is a tutor messenger. So on your phone, you can send in messages, questions, queries, clarifications, whatever you need, just using your phone or laptop if you want to do it on your laptop. And there are additional support tutors available to answer your questions if needed. And you can ask as many questions as you like from your phone so that we don't have to interrupt the flow of the day or anything. You can just ask all your questions whenever you think of them in your brain, and then you don't have to spend a while trying to remember your question whilst listening to other things as well. So really, really useful. And that's for both live stream people and in-person people. So for both of you. So if you're at all interested, we have, like I said, it's in person, or it's or you can live stream it via Zoom. It's literally a live stream of the event, I guess we should say, on that's going on. So you do get the same experience. Obviously, you're just not there in person. You're just watching it through a camera. And just move that out of the way. Like I said, we're doing physics, maths, chemistry, and biology. The dates are here. So please feel free to have a look and see which ones you might fancy doing, you might fancy coming to. There are what they called discounts available if you do more than a couple. So if you want to do, I can't remember actually what the discounts are, so maybe I won't say that, but there are discounts if you want to do more than 3 or something, or more than 4. There are discounts so that you can get some for free as well, to make it easier, obviously. So if you're year 13 and you want to do both the year 12 and year 13 course for more than one subject, then there are discounts available. And if you are just a year 12, then of course you can just come to all of the year 12 sessions if you wanted. And again, there are discounts available depending on how many you do. Okay, please, we don't have time to do it now because I have just run out of time, which was inevitably going to happen, but never mind. But please do, if you are interested at all, even in just finding out a little bit more about it, head over onto snapprovised.co.uk/seminars. There's more information over there about what we're doing. Then we can, you can get some more information. You can also send us a message. So you can send us an email at hello@snapprovised.co.uk. And if you want to find out more info and ask some questions. And yes, does anybody have any other questions before we disappear? I've seen there's lots been going on in the chat, which I haven't been able to keep up with. Amara, you said, is there a full list of topics you've already done lives on for biochem, maths and physics? It would be good to see. I don't have a copy of it. I'm sure if you just go onto our YouTube channel and then click on the uploads, I think it is it uploads? There's a section, isn't there, that just has all the live web classes on it. So I think you should just be able to kind of flick through and have a look at those, but I don't know if there will. Melissa, that's very good feedback, actually. We will. So do you mean in terms of, yeah, no, that's great. It's always good to give feedback. So could you just clarify what you meant about the topics being more evenly spread? Do you mean spending a little less time on the basics and a little bit more time on the complex stuff? Is that what you mean? And Catherine, you said, is it mass over MR to work out moles in the last few questions? So again, great question. Thank you, Catherine. So whilst we're getting other stuff for that. Mass with our equations, the way that I remember it is if you remember the definition of molar mass, which you do need to know, because you need to be able to quote the definition of molar mass. Molar mass is the mass of 1 mole. Mass of 1 mole. Or if you rephrase it, it's the mass per mole of a substance. So molar mass is equal to mass per mole. Is a way to remember it. You don't have to remember it like that. The other way that especially year 13s like to remember it is if you've been introduced to the topic NMR, is they remember that mass equals NMR. So mass is equal to the number of moles, times by the molar mass. So that's a way to remember it as well. No, sorry, Amara. You have a look through our biology videos that we've uploaded, but there are a few. There might be some on the synoptic essay, but I can't think of any off the top of my head. And there's definitely no live web classes on it, but there might be a video. If you have a flick through the archives, as it were, you might see something, but I don't know off the top of my head, I'm afraid. Cool. Thank you for that feedback, Melissa. That's great. Lovely. So acid anhydride, super quickly, just to finish that. An acid anhydride is 2 carbonyl groups with a single bond O in the middle. Yes. And then stuff going on either end, obviously. That's an acid anhydride. For the LIN3, what do we work out first? That's a good thing, actually, is always see if you can work out the number of moles of something. So there's nearly always something that's got either a molar mass, So you can work out the molar mass using the periodic table, or already given you a moles and a mass. So here we've got a mass of LiN3, and we've got a volume of ammonium nitrate. So if you've got a mass of a given formula, you can work out the moles, because moles equals mass over MR. Does it? Yes. I didn't believe myself then. So, and you can work out the MR because you've been given the formula. So that's always a good thing to look out for. If you've given a mass of a named thing, then you can work out the moles. So that's a good thing to look for. Exactly. Yep. And then look at your reacting ratio. Well done. Exactly. And then go from there. Yeah, bro. Okay, I'm gonna have to disappear because otherwise I've gone way over, and that's not fair on people that are also working. So have a lovely rest of your weekend. Good luck if you're doing some revision at the moment. Good luck with mocks as well. Really well done for those of you that stayed to the end and that have been contributing so brilliantly. You are fabulous. I will see you. Keep an eye out for our next ones. There will be other live sessions coming up. So just have a look at the schedule and see if you can see when they appear. There will be one in about a month's time, approximately, maybe just over, maybe just under, but we'll see you very soon, hopefully. Thank you very much, everybody. Bye. Ciao.